shows us sort of a diagram of what the ancients believed to be the configuration of the universe. So everybody wants to know, what is the universe like? What is their place in it? And the ancients believed that the earth was the center of the universe, and earth was the middle. Above the earth was water, above the water was air, above the air was fire, and everything above the fire was the heavens. Okay? And so they realized that there's a fixed constellation of stars. So if you go out and you look at the sky at night, you'll see a pattern of stars, and we don't really know the stars very well because we don't spend much time laying out looking at the stars. But in another couple of weeks, it's going to be dark at 4 p.m., right? And if you lived 1,000 years ago, there were no lights. You stared at the stars all night. You knew the stars very well. And so there were these fixed stars that seemed to rotate around the sky. And then there were these things that seemed to wander amongst the stars. They were different than the stars because they weren't always in a fixed place. So they were called wanderers. Anybody know what wanderers is in Greek? The Greek word for wanderers? What? Planet. That's right. These are the wanderers. It's like Naomi during first period. And then out here was the fixed stars, and the sun went around the earth. Okay? And that was the dominant view in the Western world of the way the earth is for thousands of years. When we started to emerge from the Middle Ages and science started blossoming and people started doing experiments and trying to figure out what's going on, it turns out there's some problems with the way this is set up. There's some things that can't be explained by assuming that the earth is the middle and the sun is going around. Okay? We'll talk about some of those on Friday. But Newton set about to figure out, how does this thing work? So the legend is that, Newton's sitting under a tree and an apple hits him on the head and he goes, "Whoa, gravity." That's probably not really true. Newton would not have been surprised if an apple fell off a tree and hit him in the head. Jesus would not have been surprised if an apple fell off a tree and went to the ground. Go back as far as you want in time. Ever since you were babies, you knew that when you dropped things, they fell. That's not a surprise. What Newton's understanding or his contribution was, he knew that that apple was accelerating. And he had already worked on his laws of motion. And he knew that an acceleration required a force. So to Newton, the question wasn't, why does the apple fall? What is the force making the apple fall? There's got to be a force on it. The apple is not going to the earth because that is its natural place. It's not like waking up and going, "Oh, I'm surrounded by air. I don't belong here. Let me return to the earth." Right? The apple falls because there's a force on it. And he called this the force of heaviness, which in Latin is gravitas. So the force of gravity, the force of heaviness. Okay? So that's kind of where the word came from. So Newton is the first one who, at least in writing, understood that there must be a force acting on objects which pull them towards the earth. Okay? Now, we kind of did this little simulation yesterday in lab, right? And we figured out a couple things that sort of Newton was kind of onto. The force acts between all masses, but the force is incredibly small. You don't notice it unless one of the masses is enormous. Okay? So, what is enormous in our neighborhood? The earth. So we notice gravity. If you step off a cliff, you notice gravity. Not because your mass is that big. Okay? If we put another you 10 feet away, it's not like you'd go whoop that way, right? You notice gravity because one of the masses is huge. Right? We don't really notice it between two other objects because it's so small. And Newton also realized or reasoned that the force of gravity must be diluted by distance. So here's a thought experiment that Newton was engaged in that kind of helped him think about it. Imagine you had a light bulb shining light. And you shine the light on a panel right here. That panel is a certain brightness, right? What if you move that panel twice as far away? What happens to the amount of light that hits that panel? It's less, but how much less? Well, if you go twice as far away, that light that would have hit this panel is actually spread out over 4 panels. So each panel only gets a quarter as much light. Does that make sense? You can do the same thing with spray paint. Imagine spray painting something and holding something close and holding it twice as far away. If you go twice as far away, you get 1/4 the thickness of spray paint. Okay? So as something spreads out in all directions, it gets diluted. And it's an inverse square law. If you make the distance, instead of 1 meter, you make it 3 meters. Now that same amount of light, instead of hitting one panel, hits 9. So the amount of light that hits any one panel is 1/9 as much. So as the distance gets bigger, the amount of stuff hitting the surface gets smaller, and it's proportional to the distance squared. Going 2 times farther is 1/4. Going 3 times farther is 1/9. Okay? So that's kind of what led Newton to the idea that gravity must somehow be diluted by distance in the form of an inverse square law. Okay? And that's what you guys found in lab, on part B. You found that the force of gravity was proportional to 1 over the distance squared, right? I'm going to use R, but D, same thing. It's the distance. You'll see why we use R in a little bit. Okay? We also figured out in lab that if you have twice the mass, you got twice the force. The force was proportional to the mass, I think. We figured that out in part A. Okay? And we know that if you've got an apple that has a certain mass, gravity pulls it with the force. If you have a bigger apple, there's more mass, there's a bigger force on it. Okay? Even though its inertia causes it to fall at the same rate. There's a bigger force on it. So Newton understood these two things. At least he proposed that that's how it worked. He couldn't do the experiment. It was too delicate. He didn't have the instruments. But this is the thought experiment. So Newton proposed that gravity, the force of gravity, looks like this. Okay? And on Friday, I'll show you how we know he's right. Okay? But you're going to have to wait. So, we're going to put this in our toolbox. So this is the universal law of gravity. The force of gravity, F sub G, equals capital G times M1 times M2, all divided by R squared. And you probably don't need to annotate everything there. By now you know M is mass, right? You know F is force in newtons. The thing you need is this constant G. It's the proportionality constant for the units we use. Newton didn't use newtons and kilograms. We didn't use newtons for force until after Newton. But in the units that we're using, G turns out to be this 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay? So that equation has in all those relationships that Newton proposed. We're going to call the two masses M1 and M2, but sometimes we use capital M and little m for the two masses also. That won't throw you too much for a curve, right? By the way, what happens if I give you the distance in miles? Convert to? I will get some of you on the homework on that. You'll get the x 5 times and bang your head on the wall. And then you'll ask a friend and I'll say, oh, did you convert the miles to meters? All right, so there we go. That's the equation we're going to use. So, a couple questions about it. We're just going to think about the conceptual relationships here. What would happen to the force of gravity, F, if nothing changed except M got bigger? It would get bigger, right? They're directly proportional. You see that? If M1 were to get twice as big and nothing else changed, what would happen to the force? They get twice as big. So we say that the force is proportional to the mass. Okay? How does the force of gravity depend on R? So this was the conclusion from lab.
So R gets bigger, but R gets smaller?
Yeah, they're inversely related, right? As one gets bigger, the other gets smaller. And in fact, it's what we call an inverse square relationship. If R gets 2 times bigger and nothing else here changes, what happens to the force? It gets what? 4 times smaller. 2 squared. What if r gets 10 times bigger? We go 10 times farther away from the Earth. What happens to the force? If r gets 10 times bigger, it gets 100 times smaller. 10 squared, 100 times smaller. Does that make sense? All right. So here's an example of a calculation we're going to do. If I've got 2 objects, a 50 kilogram mass and a 75 kilogram mass, so these are some pretty hefty rocks, and they are 2 meters apart. What is the force of gravity between them? Well, I've got 50 kilograms and 75 kilograms. The distance between their centers is 2 meters. We always use the distance between the middle of that guy and the middle of that guy. So even if they're touching, is the distance between them 0? No. The distance between the centers. And we want to know the force. So we're just going to plug in this. Okay, we're just going to evaluate our expression to find the force. Now, here's where things got a little sticky on the warm-up. So let's, everybody plug that in your calculator right there. I'm going to walk around and check your answer. I want you to do it in one line. Don't do any of this. This times this equals. Last answer times this equals. 2 squared equals. And then this answer, just do it all at once. Just one time. Stick it in. Go ahead, get an answer. I want to check and see how we can do it. Didn't mean to scare you. Yep, that's right. You guys agree? Yep, that's right. Okay, you got a problem. But you can't see what's after that, right? So put the scientific notation. Put it in here. No, go back here. Go back here. So if you go, see where it says science here? Hit second, and then that. Go to scientific notation, get after. There's your answer in scientific notation. So see, it was rounding, it couldn't show it, right? Right? Yeah. Keep going. You got it? Yeah. Oh, you got problems. You can't see the rest of them, right? So go to scientific mode. Hit second. And then that one. Go over to science. Scientific mode. Enter. There it is in scientific mode. And now you can see all the rest. You got it? All right, I think when you plug it in, you get 6.3 times 10 to the negative 8. Okay, that's the wrong E. It's not a lowercase c. You've got to do 6.67. Your E is shift that. E to the negative 11. And you go times 75 times 50 divided by 4. You got it? Good. Your E is there, yeah. But now you're overloaded. You got it? So it's your 6.67. Your E. 10 to the negative 11. You add up your exponent. Times those 50 times 75 divided by 2 squared. Now, you can't see the rest of that, right? So I think you've got to go to mode here. And go down to scientific. And then you do that. And this calculation. You see the answer is, so now you can see it's actually 6.25 times 10 to the negative. All right, I think we mostly got it. All All right, so this is not a very big force, guys. That is 6/1000th of a Newton. If you take one little measly cheeseburger from McDonald's and divide it, just the burger, not the meat, not the bun or anything, and divide it into 1,000,000,000 pieces and take 6 of them, that's the force of gravity between two objects in our normal world. It's tiny. We don't notice it. Okay? All right. However, if one of the objects is really big, you do notice gravity. So let's do another calculation. We got Sally here. Anybody wear cute pink skirts with polka dots when they were little? Who said yes? Laura? All right, we'll call that Laura. There's Laura, the 4-year-old version of Laura. And we want to know, what is the force of gravity between Laura and the Earth? Okay? So, we have to know a couple things. We got to know the mass of Laura. We got to know the mass of the Earth. And we need to know the distance between them. How far is it from the middle of Earth to Laura's belly button? Okay? Now, do we need to know how tall Laura is? Laura's 4-year-old self? Well, here's the problem. We only know the radius of the Earth is 6.378 times 10 to the 6th meters. That is 6378000 meters. Where is the uncertainty in this number? According to our rule of significant figures, where's the uncertainty? Lady? The 8. We are uncertain of the 8. If we knew the 8 for sure, we would write it and the next one that we were uncertain of. That's our rule. We always write all the digits we're certain of, and the last one we write is the one we're uncertain of. That means we are uncertain of this. It could be a 9,000 meters, or it could be a 7,000 meters. We are uncertain of the radius of the Earth by a couple thousand meters. Does it matter whether Laura is 3 feet or 3 feet 6 inches tall? If we are already uncertain by a couple thousand meters, that's a couple miles, right? You can go to the top floor of the highest building in Indianapolis and still not even be close to the uncertainty of the radius of the Earth. The Earth isn't actually perfectly round. It's oblate. It's got a big wad of jelly, and it was perfectly round, and you spun it, the middle would push out a little bit because of its inertia. So the Earth is not round completely. So we're gonna say we don't really care how tall Laura is. We're not going to worry about the distance from her feet to her belly button. We are already uncertain by 1,000 or 2,000 meters in the radius of the Earth. Okay? All right. So let's calculate the force of gravity on Laura. Here's Laura. Here's our variable list. Here's the calculation we're doing. We're just going to evaluate g m1 m2 over r squared. And now we got to plug in these numbers. And here's the hint, guys. Do not use parentheses for multiplication. I put them here so you can tell where the numbers are. But take 6.67 e to the negative 11 times this times that, and use parentheses for grouping. Group your numerator and group your denominator. Okay? Go ahead and evaluate that expression on your calculator and see if we can agree with it. I've saved them for you. You don't need to put them in your notes. See if you can evaluate that expression and get an answer a little less than 500. That's how you know you're right. Using parentheses. You don't need to group that. You can convert. You can do that. That times negative 6. It doesn't truly multiplication. All right, did you get 490? I think. 490, that's right. You want a time notation? It's right there. Just highlight, use your arrow, you hit enter. So it's 4.9 times 10 to the second. All right, so when you plug all this in, you get 490. That's good? That's good? You got it? You get that there? All right, so that's how you find the force on Laura. Now, what if we want to solve a different problem? We wanted to find the force on Damon. And Damon's 80 kilograms. What would change about this problem if we were finding the force on Damon instead of Laura? The only thing that would change would be the 50, right? What if we were trying to find the force on a car that had a mass of 2,000 kilograms? None of this would change, only that, right? So, because we solve a lot of problems on the surface of the Earth, let's go ahead and calculate what this part is for Earth. Okay? Because none of that is going to change for finding the force of gravity of something on Earth. So, take these numbers. Here's the mass of the Earth. Here's the radius of the planet. And here's G, the universal gravitational constant. Go ahead and calculate that, and then we'll know what we need to multiply the mass by. We just shortcut, right? So go ahead and plug those numbers in there and see if you can find out what this magic number here is that we can use on Earth. Plug them in. A lot of calculating today. Got it? Huh. Nope. Okay. You didn't group your denominator and you didn't square it. And you got to group it too. Otherwise, you just divide it by this and then multiply by 10 to the second. Huh. See that number 4? What's the problem with filling in parentheses? There is no problem. I didn't say you couldn't do it. I said it's a bad idea. If you use parentheses for multiplication, then you're not using them for grouping.
Yes.
You need a group. So if you do this all correctly, you should get a number that either surprises you, or you should have been expecting it all along. Did you get 9.81? That's what we've been doing all along. Look back at Unit 2. Look at your toolbox in Unit 2. How do we find the force of gravity on an object? In Unit 2, we had Newton's law, and then we had how to find the friction force and how to find the gravity force. We took M times G. We took the mass of the object times G. And that worked where? I kept saying, on Earth, right? When you go to Mars, you got to use a different value of G. Now you know where that comes from. That's just applying Newton's law of gravity to problems where the mass of the Earth stays the same and the radius of the object, the distance between the center of the Earth and the object stays the same. And if those don't change, then you can just calculate that as 9.81. So if you want to know what's the mass of Laura or Damon or anybody else, just take 9.81 times their mass. Because this whole mess here, this whole mess right there is 9.81 for Earth. Then you just multiply by the mass of the object. Okay? So, big G is the universal gravitational constant. It works anywhere in the universe. But you got to know the two masses and how far they are apart. Little g is our local gravitational constant. It only works on Earth because we calculated it using the radius of Earth and the mass of Earth. If you go to a different planet, you can calculate g on that planet. You just need the mass of the planet and the radius of the planet to calculate it. So that leads us to a second equation, which really isn't a second equation. It's the same equation we've been using. It's just part of it. Little g, the gravitational constant on a planet, is simply big G times the mass of the planet divided by the radius of the planet squared. Okay? That's exactly what we did here. That right there is little g. Okay? So what would happen if the radius of the Earth got 2 times bigger and nothing else changed? It's like somebody roasted the Earth like a marshmallow, and the same amount of mass just got bigger. What would happen if the radius of the Earth got 2 times bigger? What would happen to G? We get 4 times smaller. We'd be close to 2.5. And that'd be really cool, because you could jump 4 times as high. Yes?
So what is big G?
What is big G?
Yeah.
What is this?
Yeah.
It's always 6.7.
So it's always that hot.
Yeah, that big G is the universal gravity constant for anywhere in the universe.
Okay.
And it appears to hold true even when we look at happenings in distant galaxies. All right, so let's kind of tie this up. Newton proposed an empirical formula or description of gravity. Newton had no clue how it was the Earth pulled on the apple. He didn't know the mechanism. He just knew how to describe its effect mathematically. We call that an empirical formula. The ideal gas law you learned in chemistry is an empirical formula. When it was developed, people had no idea what the heck temperature was. They didn't know that even matter was made of atoms. But it described relationships that they could measure: pressure, volume, temperature. Okay? So an empirical law is one that explains things mathematically, but we don't know why it's there. We know the ideal gas law now. We can derive it. It's kind of funny. But actually use momentum impulse transfer to derive the ideal gas law. But that's for later. Einstein set out to propose a mechanism for gravity. Not just how do we describe gravity, but how does it actually work? And I'll show you that in a minute. Okay? So Einstein proposed this mechanism for gravity, and it was called the general theory of relativity, and he received the Nobel Prize for that. He developed the theory in about 1930. It made some wonky predictions, which weren't first confirmed until 1957, and then some of his other predictions about gravity waves, we actually didn't measure those until 2018 with the LIGO detectors, which are in Louisiana and Washington State. We measured gravity waves for the first time, coming from the collision of 2 distant galaxies. And the guys who measured that got the Nobel Prize in 2018. Okay, so we're still confirming some of the things Einstein predicted. So let me show you kind of how Einstein's theory works. So I need you guys all to stand up and help me here. So let's see. Josh, see if you can make a video of this for the absent people. Just move it down. Okay, everybody come stand around here and grab an edge of the cloth and hold it up. We need this tablecloth level. So I got there, Anna. Everybody grab a piece of it and hold on. You need it level. Grab down there. There we go, there we go, there we go. Grab on. Everybody hold up. Okay. Move over here. All right, so here's what Einstein proposed. Hold that.
There's a bag and a table.
Yeah.
Here's what Einstein proposed. Einstein proposed that space is like a fabric. You may have heard the fabric of space. That comes from Einstein. In fact, it's a 4-dimensional fabric and composed of space and time, okay? And what Einstein said is that matter warps the fabric of space. So if I put this on here, it causes the fabric of space to bend a little bit. You see that? Your space-time isn't quite level here, guys. Now, if I put this near it, what'll happen? Why does it go towards it? Is that ball pulling on this ball? Or is this ball just following the curvature of space? Yeah, that's what's happening. What happens if I put a bigger mass there? What does it do? It curves space more. Now, here's one of Einstein's predictions. Einstein said that mass curves space, and that light will travel through the curvature of space. So if there's a star over there right by Chloe, and that star was shining light, and I'm over here, should I be able to see the light if that was the sun? I shouldn't be able to. But some of the light from Chloe might go, some of the light from Chloe might go this way and curve around it. And in 1957, some astronomers traveled to Australia for an eclipse so that when the moon blocked the light from the sun, we could see the light from the star sneaking around the edge of the sun, which proved that light curves. It follows the curvature of space. So here's our sun in the middle, and then if you have something like the Earth doesn't cause much of a divot itself, right? But it will follow in a path around the sun. Now fortunately, the Earth doesn't lose energy as fast as the golf ball does. But you guys have put the quarter in the machine at remember the mall? Those things we used to go to?
I think they're still
You put the quarter in, the quarter goes around and around and around? Is the hole sucking the quarter in, or is the quarter just following the curvature of the well? That's why the planets go around and around. That's how gravity works, okay? What would happen if I made this ball heavier and heavier and heavier, and denser and denser and denser?
You eventually start sinking it.
It would actually rip the fabric of space-time, and we would have a black hole. And if this thing were to rip the hole that just disappeared forever, what would happen if something rolled towards it?
It would get stuck in there forever.
It'd be gone. What happens if light went that way? There's no path out, right? That's why it's black, because no light returns from it. So a black hole is a rip in the fabric of space-time. And if you want, you can think about the alternate universe on the other side of ours, and the black hole connects to a white hole with a wormhole. So maybe if you went into a black hole, you'd emerge in another universe. All right, thanks. Or you'll just get shredded. Your atoms will get all pulled apart.
Or you just get stuck in there forever, and then you die.
Can you hold this for 5 minutes?
And I'm not gonna be the one to try that out.
Oh, good.
Oh my gosh.
All right, so we will talk about orbital motion and circular motion and how rocket physics works on Friday. But for right now, we're going to solve some problems with gravity. Okay? So grab your computer, find your problem set. And the first 2 questions are conceptual. You don't need to show any work.